Hello everyone. Today I'd like to introduce our work, Incremental Context-Free Grammar Inference in Black Box Settings. Consider some examples and we try to find a grammar describe the examples. And the grammar that we use to describe the example is the context-free grammar. Context-free grammar is a collection of terminals, non-terminals, and production rules. And terminals are literals that appear as is in streams, such as a or one. And the non-terminals are replaced as described by a rule, such as we can replace the factor to by 1 or a, and we start from the non-terminal expression and replace the non-terminal into a rule, and we can describe a language. Our work is based on some examples and a work. We can check on inputs validity by the work. Here is a valid input, and here is an invalid input. And we try to infer a grammar from some examples and a work. The workflow of our method that's called the Kadawa is as follows. First, we tokenize the example streams and then we decompose the examples into simpler components. And finally, we infer grammar from the simpler components incrementally. First, we will tokenize the example streams, and we use the proposed pre-tokenization applies common lexical rules to segment the example streams into tokens such as identifiers, streams, and numbers. And then we consider that two tokens can be merged if we swapping them in all their occurrences maintain the validity. And finally, we will generalize the token's value, such as we generalize the a into a, b, c, and some other lowercase letters. And then we propose breaking down complex example strings into simpler components while collectively preserving all grammatical structures of the original program. For each example, we try to remove a fragment of example and keep a given token. And we repeat this step until we cannot remove a fragment anymore, and we can decompose the examples into simpler components. Here is the incremental grammar inference of our work. We build grammar from the decomposed sequences, and first we choose a shortest example from examples, and then we will find the bubbles to merge, and then we can generalize the grammar. The first step of incremental grammar inference is bubbling. The purpose of bubbling is to identify parts of the grammar that can be generalized. Algorithm 3 outlines how the bubbling step works. First, we consider all subsequence of the rule, and we need to generalize. And then we swap them with the subsequence of other word production rules, and if they can swap, we record it. And finally, each bubble set is corresponding to a possible generalization of grammar. Then we will choose the most generalizable bubble sets algorithm for outlines how to calculate the bubble set score for choosing the most generalizable bubble set. It means if we merge the bubbles, we can obtain more generalization. We choose the bubble sets that has the highest generalization score, indicating the potential to produce the most generalizations. And how to estimating bubble set score? First, we calculate or generalize the examples by swap. And then we estimate the generalization score by calculating the acceptable number of generalization samples after merging bubbles. And before merge all bubbles, we need to eliminating overgeneralization. And the bubble sets selected in the previous step only explains whether one bubble is swappable with other bubbles. However, we did not check the bubbles generated from the existing grammar are swappable. Merging these unswappable bubbles may introduce overgeneralization. In this step, we aim to select a subset of bubbles that maximize generalizability without causing overgeneralization. And algorithm 5 outlines our methods for this step. Finally, we merge all bubbles and simplify the grammar. After iterating all sequences generated from the example strings, we identify the repeatable bubbles within the grammar. If a sample generated by the repeatable bubble is accepted by break, the bubble is marked as repeatable. And then the final step involves expanding each terminal in the grammar to a larger character class based on the character level generalization table. For instance, we expand T1 to ABC and some other lowercase letters. Then we will introduce the evaluation of our work. We use the benchmarks most of our previous works, such as learning highly recursive input grammars ASE 2021 and fast deterministic black box context-free grammar inference ICSE 2024. The first question is that does Kdawa infer better grammars than Trivad and Avad on the same dataset? Through experiments, we found that Kdawa has a better F1 performance than Trivad and Avad on most datasets. The F1 score measures the trade-off of precision and recall, and Kdawa shows a high precision of 1 or close to 1 on almost all datasets. And the second question is that is the runtime of Kdawa lower than Trivad and Avad on the same datasets? through experiments, we found that Kadawa has no significant increase in memory usage, and Kadawa's average runtime significantly decreases. And the third question is that how compact are the inferred grammars? Compared to the Trivada and Avada, we have reduced the number of the non-terminals in grammar and the total length of the rules to about half of the original amounts. In conclusion, we introduced Kadawa, a novel approach for context-free grammar inference in black box environments, and we introduced a new data decomposition and infer from decomposed examples incremental. And then we compare the performance of Kadawa against the short-term approaches, Avada and Trivada. Our results indicate that Kadawa significantly outperforms these benchmarks in grammar quality, readability, consistency, and computational efficiency. That's all. Thank you.